Hello, good morning. So welcome to the tutorial. So today we will talk about exam 2 solution uh, and then happy Dragon Boat Festival. So let me start. Eh? How come? So I should start this one. Yes. Okay, so for question 1, it is about a game show problem. So we are having n by n boats. They are arranged in a 2D array. So the contestants are located at the bottom part of this area, and then the target is like this. So they can pick one of the boats in the first row, select it, and then jump. So let's say the contestant select this one. The next step that he can do here is that he can select one of the boats in the northerly direction neighboring to this one, like this one, or this one, to move. And then maybe after this, let's say he chooses this one, you can select this one, or this one to move, and then maybe moving like this, and then moving like this, and then reach the top bank. And then, so we have the boats here, so we can label the boats like this is B11, B12, B13, this B21, B31, B41, B51, something like this. And inside each boat, there are some gold coins. So for boats BIJ, let's say there are gold coins GIJ. And then we want to find a way that the contestant can start from the bottom row, choose a boat, and travel along so that along the way he can pick up the most number of gold coins. So how can we do so? So this is a dynamic programming problem. So we can solve it by something like this. So let us define Mij to be the maximum number of gold coins when the contestant can reach both Bij. So in that case, we will get the gold coins at the both Bij together with the best way that he can reach before this boat Bij. So so suppose that gold coins there is no negative value, so all of them are positive. So for I is equal to 1, then in that case, Mij will be equal to Gij. Is that okay? So if it is on the first row, so you can only pick the corresponding boat to reach that boat. So in that case, whatever money that you get in the boat is the maximum coins that you can get. So when I is equal to 1, we have this relationship. And for I is greater than or equal to, greater than 1, then what will happen? So for instance, something like this, suppose that what is the maximum number of gold coins that I can obtain if I can reach this boat? So to reach this boat, either we are coming from this one, or from this one, or from this one. So the maximum number of gold coins that we can get from this boat must be the maximum of this one, and this one. Select the maximum of it plus the gold coins inside this one. So in general, we select for I and J, we pick up the corresponding boats in the previous row. So all of them has I minus 1 here. That can reach this J. So they may be reaching from J minus 1 or J plus 1 together with the gold coins that we obtain in the boats Bij. Okay, so here we have omitted the extreme case. So when j is equal to 1 or j is equal to n, then we need to be a little bit careful, because when j is equal to 1, then this term is not defined. We are just calculating the maximum of these two instead. And similarly, when j is equal to n, then this term is not defined because it is like n plus 1. So in that case, we are only maximizing the 2 here. Of course, you can. So this is one way. Okay, so as long as the boundary cases can be handled correctly, then it will be fine. So you can also define this this when the case of j is equal to 0, or when the j is equal to m plus 1, we can define this M to be a larger matrix. So let's say these values, we can set it to be 0, or we can set it to be negative infinity. Yeah, that would also work. Okay. Now, based on the recurrence, we can see that each of the value of mij can be computed in constant time. The reason here is that if I want to compute mij, I can take out this value, and this value. So these values are already there. So we can get them in constant time. And then adding up to the Gij value also takes constant time. So in that sense, the total running time will be what? So there are n variations for the value of I, n variations for the value of j, so there are n squared terms in the entry, and then each one of them computed in constant time, so the total time is n squared. And then how do we get the best solution? The best solution is we look at the last row, okay, mn, and we find out which boats that we reach will give us the best number of coins. So this is the maximum of this one. So I'm here again. This tutorial is to give you the high level details. So there are still some missing parts that you need to fill in to make things very, very precise. So this is left to you as an exercise. Okay, for question 2, so we are looking at a problem that is similar to an assignment question. So we have n points. They are located on the x-axis, and then we want to cover all the points by using line segments, and each line segment is having only unit length. And then, unlike the assignment question here, we are requiring, or we are restricting that each segment can cover up to 2 points. So if I have 3 points in a closed region, I will need to use 2 separate line segments. And then we want to find out what is the minimum number of line segments that we need. Okay, so we can design a greedy algorithm to solve this problem. So what we are going to do here is we are processing the points from left to right. So if we can cover the leftmost 2 points with just one segment, then we will do so. Otherwise, we will cover the leftmost point with one segment. Now, for after this step, either 2 points or 1 point will be covered, and then in that case, we will remove the covered point or points. If there are still some points left, we will go back to step 1 and then do the process again. So we are actually making this as our greedy choice. So we greedily find out whether we can cover the leftmost 2 points with one line segment. Okay, and then once it is done, so we cover points, and then we continuously solve the remaining problem recursively. Now notice that, so before we talk about the correctness, so let us analyze the running time. So if the input points, actually in this problem, the input points are already sorted. They are given in the order from left to right, one by one. Then in that case, when we process the leftmost point, it is very easy. It is just taking constant time to check whether the next point is within a distance 1 from it. So we can decide whether we are covering just 1 point or covering 2 points in this round. So by doing this, the processing time, every time we are removing at least 1 point. So in that case, there are n rounds at most. So the running time is order of n. So running in order of n will let us know how many line segments that we need. And then to show, so we are going to see that the greedy choice works. So this can be shown by using the cut and paste argument. It is not easy, okay? So we need to be careful how many different scenarios that may happen. But once the greedy choice is proven to be correct, then the algorithm will be correct automatically, because it means that there exists an optimal algorithm that is doing the same thing as we do in the first round. So in that case, we focus on those algorithms that do the same thing as we do. And so after that, we are left with a subproblem of the same type. So we can solve this recursively. So in that case, our first choice matches with certain optimal algorithm. And then by doing this choice, the remaining part will be to see how we can do the best for us, and so we can solve it again using an optimal algorithm. And that's why we can solve it by greedy algorithm, by making the greedy choice one by one without any mistake. Okay, for the greedy choice, I'm not going to show it here fully, but then we can see that what are the cases that we need to consider. So for the greedy choice to work, okay, we need to consider what happens if a certain optimal algorithm doesn't do the same thing as we do. So what are the cases that we must see? Okay, so first of all, if the leftmost point is far away from the second leftmost point, then we will see that no matter what we do or the optimal algorithm is doing, we must both cover this point with only one line segment because it cannot be shared with another one. So in such a case, then both our algorithm and the optimal algorithm will make the same decision. So in this case, it is an easy case. Now a different case is, okay, when the two leftmost points, they are close to each other. Okay, for our case, we are covering them with the same line segment. In an optimal algorithm, it may not be doing so. For instance, in the optimal algorithm, it may just use one line segment to cover the leftmost point only without covering the other one. Then in that case, we can easily see that we can change the optimal algorithm by putting the second leftmost point together with the first leftmost point, just taking it here to be covered at this time rather than in a later time. And in such a case, the total number of line segments does not increase. So in this case, we can safely convert a certain optimal algorithm to another optimal solution, not optimal algorithm, optimal solution to another optimal solution which has the same decision as we do. So this is also a case easy for us. And the third case that will happen is, what if in the optimal algorithm, it is trying to cover the leftmost point with some other point, not the second leftmost, but some other point instead. Then in that case, we are going to do the cut and paste. We are going to exchange the points that is covered in the optimal solution with the second leftmost point. And then after the switching, we can see that the total number of line segments does not increase, and then it is still also a valid solution, so we can still get an optimal solution. So I hope you understand what I'm talking about so far. So here, the tedious part for this problem is not just the design of this algorithm, but it is the argument that the greedy choice works. Okay, so let me double check if every one of you are okay so far. Let me see. Okay, so far so good. Okay. So let me go back to the slides here. Okay, the next question is the amortized analysis question. So here we have a binary counter, and then this binary counter support two types of operations. The first one is the same as the lecture notes. We have increments, so we can increment the counter value by 1. But then we have also something called the 2 power increment. So for this one, we can increment this by some 2 power. The cost of an operation is depending on the total number of bits that is being flipped or changed. And the initial value is equal to 0. And then we want to show that the amortized cost for each operation is only constant. So the easiest way actually is by potential method, but then the more intuitive way is by using a counting method. So what I'm showing is by using a counting method. So we will maintain the following invariant. We will make sure that at every step after an operation, the following red thing holds. So it says that each bit 1 inside the counter value has $1 associated with it. This $1, this money is going to be used to pay for any future flip of this bit. Okay, so this is similar to the exact, or actually exactly the same kind of money that we need to reserve for the original binary counter problem. So we are going to maintain this invariant. So initially, the counter value, initially the counter value is 0. So, and then we don't have any money, so that's good. So each bit 1 has $1, so it's good because we don't have any bit 1. So every bit inside the counter has no money and is all correct. And then how can we maintain such an invariant? So here what we are going to do is for each operation we are going to pay $2. Now no matter we are doing the increments or doing the increments by a 2 power, each increments, these types of increments operations will invoke a series of flips, but then only one of them is flipping a 0 to a 1. So it is easy to check that whenever you add a 2 power whose binary representation just has only one inside the bit pattern and increment 1, okay, then it is still just having one of the bit 1 inside. So when you add a 2 power or add the value of 1, then the addition will have carries maybe, but then it must be in the following pattern. You may flip some bits from 1 to 0, some bits from 1 to 0 in a series of flips, but then there will be only one of them, the last one, will be changing from 0 to 1. So all of them are 1 to 0, except the last one, which is 0 to 1. Now when it is all, for all those 1 to 0, so we recall that if there is a 1 inside the counter, it has $1. So this money is now paid to do this flipping operation. And for the last step, when we change it from 0 to 1, we are paying $1 from the money that we have. We have currency $2, right? So $1 is paid by actually carrying out this flipping operation, and then $1 left is now put associated with the 1 bit that is inside this counter. So in that case, we will see that the money is always enough to pay for every operation. And so each operation will have $2. N operations, we have order N dollars. So the amortized cost is order 1. Okay, next is question 4 and 5. But then these two are just simple questions about binomial heap and Fibonacci heap. So you can work it out by yourself easily. Finally, it is question 6. So question 6 is a dynamic program problem, very similar to the assignment question, but then it is slightly harder. Okay, so let's see. So this time we have a rooted tree. There are n nodes. Each node there is a positive cost. So here we are talking about, like, we have a city, looks like a tree, and then we want to set up convenience store at locations to serve the citizens. So, but opening a convenience store need to, at a certain location, needs to pay for some setup costs. And then we are going to color the node V, which means that we are going to set up a convenience store at the corresponding node by paying the cost of V. And then the requirement here is that we need to serve all the cities, okay, all the buildings inside the city. So we need to make sure that for any node, either a neighbor of it or itself has to be colored. So we need to make sure that every citizen can visit a neighbor, can visit a convenience store easily, either from its own building or from a neighboring building. So we want to set up the convenience store so that we want to pay for the minimum total cost. So we want to color the nodes. Color means setting up the neighboring store. So here, two neighboring stores could be adjacent to each other. That's also okay. So we don't have any restriction about whether I can open a store next to another one. It's perfectly okay. The only requirement here is we need every building to be served. Okay. So we can solve the problem like this using a similar idea as the assignment questions. So for each node V, we use T of V to denote the subtree rooted at V. And then we use best of 0V and best of 1V to represent if I want to just focus on the subtree TV so that every node inside this TV is being served. So best 0 corresponds to the case where I'm not going to set up a store at V, and best 1 means that I'm going to set up a store at V. Is that okay? So this is the difference between these two. Something okay. Something wrong here. So let me change it a little bit. Okay, so what is the okay? I was making things yeah, it's something wrong. So how do we compute best 1V? Best 1V is like we need to pay for the cost of V because we are now setting up a store at location V. So we need to best 1V means that we are setting up a convenience store at location V, right? So we need to pay for the cost of V here initially, but then for all the neighboring child, because this is already covered, so we don't care whether we need to so this is so in that case in let me double check if I'm correct. Yes, in that case, there may be something. I guess this is correct, but let's see. So here in that case, for all the child, so this is to cover the node V, and then because we have now a convenience store at this location, we can either set up or not set up a convenience store at any of its children. So in such a case, we need this for each child C. We can either pick the case that we do not open a convenience store at C, or we pick the choice of opening a convenience store at C. Either way is fine. So the best way to serve the subtree TV when we set up a convenience store at V is like this. So best of V is like this. Is that okay? Okay, now the tricky part is best 0 of V. Okay, best 0 of V. Best 0 of V is this one. So best 0 of V is like what? Okay. So I'm doing something tricky here. Okay. So because we are now, so for best 0 of V, so let me turn on this slide. Because when it is 0, that means that we are not opening up a convenience store at location V, but then V has to be served. Then that means that we need to find out one of the children of V to serve it. So in such a case, we first find out which one is the best child that we hope to use it to serve it. So here, what we are going to do here is we are going to find out one of the child such that, so at least one of the child needs to serve it. So in such a case, we let C star to be the child of V such that best 1C is minimized. So in such a case, then we are going to use this child make sure that it is opening a convenience store and serve the node of V. And then for all the remaining children of V, we don't care. So we can compute this actually by doing what? We can compute this by finding out for all the so it's like, so the formula is actually like this. So let me write down. So what is the actual formula? But we can be a little bit smarter to compute this. So let me copy it. Sorry for the mess things here, but here this is like this. So this is actually this one. So so you can see this very clearly. Okay, so this is this one. So the way to compute the best of V when you do not open a store at location V is we find out the best child, C star, that we open a store there. And therefore the remaining child, whenever C is not equal to C star, we can select either to open a store or not open a store for this location C. So this is the answer for this one. But then you can see that the first part is exactly the best one of V that we have computed in the previous page, minus the cost of V, and then minus the best zero of C star. So this term, and this term actually gives us this term. So we can simplify this a little bit by computing the bottom part directly, because we now have best one of V. Okay, so this is clearer, but then this is cleverer. Okay. And so once all the solutions of them are known, so we will have best R when we do not open a store there or we open a store there. And then the best solution will be the minimum of these two. And notice that each of the best value can be computed using the degree of V time based on the degree of V. So the running time will be order n in total. Okay, so that's all for today. Yeah, so let's see if you have any question. Yeah, if not, yeah, that's all. So bye for today, and then for next week we will talk about the homework 5 and homework 6 solution together with the MP harness. That is not going to be covered in the in yeah. Thank you, thanks so much. Okay, so see you next time. Bye bye.